And shall we enter into the session? Yes. Okay. Yes, thanks for confirming. So as I said in the previous session, so if there is any question, so kindly post it in the chat box. So I have already started the series of answering the questions which are asked in the webinars, as because 1.5 hours is not enough to answer all those questions, right? So all those insightful questions will be answered through my LinkedIn post. I have already started, and myself and my team, right, we combinedly answering all those questions. So in case any doubt means, so kindly post it in chat. So after the webinar, everything will be saved and those questions will be answered. Right? So we can start with the session. Let me share my screen.
गोला बना दीजिए.
Just kindly confirm me that whether my presented screen is visible now. Yes. So thanks for confirming. So installation coordination. So we can start. So what are we going to see in our today's session is, so what is installation coordination and what is the need for this installation coordination, right? And what are the some key terms to be noted and the standards and guidelines what we are going to follow for performing installation coordination, like international standards, what are they? And the basic simulation setup, right? For example, I don't know whether 90 minutes is quite enough or not, but even though we can try our best, so I have already prepared a predefined system just to explain you all that simulation setup in PSCAD. So in that we can see the case example. So followed with the Q&A session, right? So now we can start. Yes, before starting, so after registering for the webinar, have anyone discussed about what is installation coordination? Yes, you can post it in chat. So even if you have previously means you can post, or else after registering for the webinar, have you checked what is installation coordination and why they are performing in PSCAD? Yes. Okay, proper relay and circuit breaker operation in coordination between upstream and downstream devices. To isolate fault, not really. Yes, over voltage studies. Exactly. Yes, my Mr. Map I will check, sir. So I will check how to share that. Yes, to safeguard our arresters, coordination with surge arrestor, yes. To check the surge arrestor rating, yes, of course. So in installation coordination, so we are going to study about what are the over voltages that can be occurred in the power system and how we are going to protect that using our installation coordination while we are performing in our PSCAD. Yes, deciding the installation level, yes. Selection and arrangement of, yes, everything is right. So the basic definition, what is mentioned in IEC 60071 part 1 for installation coordination is, right, selection of dielectric strength of equipment in relation to the operating voltages and over voltages, so which can appear on the system for which the equipment is intended and taking into account the service environment and the
Video
characteristics of
call.
the available preventing and protective devices, right? Which means, so for a power system, so that power system can be like, it can be whatever may be the plant, like a combined cycle plant, oil and gas plants, whatever it may be, right? There we have to place our protective devices, right, in accordance with, right, our dielectric strength of the equipment. So, for example, if you are placing the surge arrestor means, so it should capable of capturing and withstanding the switching and lightning over voltages which are going to occur in our circuit. Right? This is the basic definition. So selection of let me right? So selection of the dielectric strength of the equipment in relation to the operating voltages and over voltages which can appear on the system. So this operating voltages and over voltages which can appear means it can be whatever maybe like switching, lightning, so which can be internal and external as well. Like when the equipment is intended to subjected to these types of over voltages, so it must withstand, right? It should not get faulted anything or destroyed immediately. So if the switching or lightning over voltages, which is occurring internally or externally, right? If it is within the limit means, so our surge arrestor must withstand those voltages, over voltages, right? And after clearing of that over voltage, so once again our system must be entered into the normal steady state, right? So that like for we want to select the capable surge arrestor for our system, right? And taking into account of service environment and the characteristics of the available preventing and protective devices, right? Whether the device is already available means, so in case we are additionally adding any new plans means, so at that time we want to do once again insulation coordination. So once it is completed, right, or else whether we are newly going to add the surge means, so in that case also we want to perform our insulation coordination and we have to select our surge, right? So upon seeing what are the outcomes means and performing insulation coordination study, so there are various things. So mainly these five voltage levels of the power system equipment are determined. So voltage level means we can ask that already available voltages will be there. Then what this voltage level means? So during the disturbance, right? During the disturbance, like a switching or lightning or any internal or external causes, the voltage level of the power system during those disturbances can be determined, right? To ensure the protection of equipment against low voltages, as we said now, to provide the reliability of the system by decreasing insulation failures, right? So upon performing this, we can able to identify our reliability of the system and to reduce the cost of the system by preventing oversizing of the equipment. Right? For example, such as what we are selecting. So for in case if it is a 230 kV system or 400 kV, so after performing all these studies only, we have to select the rating of the proper rating of the surge system. So we cannot able to select the surge arrestor like for 230, this rating will be okay. So like that we cannot able to select in our own wish. So we have to perform this and we have to select our protective devices, or else it will be like oversizing. So upon oversizing, we know that the cost of the equipment will also be more. Right? And in additionally to prevent failures and over investment. Right? Is there any doubt up to now? So what is insulation coordination? Hope you have got some idea, right? So we are going to protect our power system, right? When externally causing disturbances. So at that time we are going to check whether our system is capable and my protecting devices is going to protect my system or not. In simple terms, so whether chat is enabled. Okay, then. So what are the standards and guidelines? So we are using for this installation coordination is. So the very first one on the preliminary standard is IEC 60071 in that specifically part 1, 2 and 4 which will be going to help a lot in our installation coordination part. Right? Whereas the first part of IEC 60071, right, it will be holding the definitions, principles and rules of installation coordination. Right? And the second part, IEC 60071 second part, it will be the application guidelines. So what are the guidelines to be adopted while performing installation coordination? Then the fourth part is computational guide, right, to installation coordination and modeling of electrical networks. So in here, installation coordination, there are different classification of studies which we are going to perform. Right? So for each study, we are going to model the same elements as a different one for different studies. Then we will see for the what element how we are going to model like that we can see.
अभी हम फिर शाम को भी हम कर
And
लेंगे.
IEC 60009
अभी लाइए ना एक काम.
which is mainly focusing on surgeon stress, selection and application recommendations. So it will also help us to adapt how to select the surgeon stress. So for that we will be using this. Then finally, when coming to IEEE part, right, this is the old one actually, IEEE 1313 in that first part. So in here basic rules only, here they will not be explaining any methodologies or guidelines. So installation coordination, definitions, principles and rules. So these all will be presented in IEEE 1313 part 1. So these are the standards and international standards and guidelines what we are going to use for performing our installation coordination study for our power system. Clear? So when coming to the causes, so the basic causes we might be aware. So the lightning strikes, right, in our power system, how the over voltages will be occurring. So it will be external or internal. Internal means switching operations. So switching operations, it can be whatever may be the switching. So any equipment in our power plant or power system, whether we are switching, right, that will also be the reason for our over voltages. Then lightning strikes, that is external cause. Then ferro resonance, then ground faults are unbalanced fault. Right, that is the faults simply. Then load rejection, when suddenly highest capacity load is getting rejected. Then improper coordination of surge arresters. Yes, so without performing installation coordination, so blindly we are selecting the surge arrestor and we are trying to enhance that surge arrestor in our system. So that time also there will be the chance of over voltages in our system. Then the effects that also we know. So what are the effects? The basics only: insulation breakdown, like the damage to the transformers. The arresters will be getting overstressed. Sometimes, in most case, flashover of bushings or switchgear, then malfunction of protection systems. Similarly, arc flash or fire hazards. Then, when continuous over voltage is impacting in our any equipment means, so that the equipment will be getting aging factor. That will also be a constraint. When the equipment is continuously getting over voltage effect means, so it will reduce its aging. So the total lifetime of the equipment will be getting reduced here. Clear? So when coming into the part, so majorly we will be classifying the over voltages for our installation coordination study as. So TOV, which means a temporary over voltage, and SFO, slow front over voltage, fast front over voltage, FFO, and very fast front over voltage, VFFO. So other than this also, there are some over voltages is there, so we can see. So before that, kindly confirm that up to now whether it is clear and everyone is in line with what we are going to see in detail. Yes, may I get some response? Yes. Okay, so we can actually add a hyperlink here. Right. So we can see one by one. So what these studies and what are the cases we will be created. So with the help of the cases itself, so we can know that what will be the causes of this temporary overvoltage, what are the causes of this slow and overvoltage like that. Right? The basic and preliminary study, so in the insulation is the temporary overvoltage, which is TOV. Right? So in this, if I am taking means, let me go one by one. So first we can see what are the cases we are going to perform in our TOV. Right? So when coming to the cases of TOV, so we will be starting with Faraday effect, like that everyone knows. Then LG fault, LLG fault, then load rejection. Right? So when any huge load is connected, higher capacity load is connected, and suddenly that load is getting detached from our power system. Right? In that case, then LG fault with the load rejection. So after occurrence of the fault, the load is getting detached from our power system. That is LG fault with the load rejection and LLG fault with load rejection. So the same case of LG and LLG will be performed here. Right? So during these cases, so what we are going to analyze is, right, these are the cases we will be creating in our TOV. So in addition to that, what we will be analyzing this TOV are, the first one is to determine the MCOV capability of surge arrest. Right? This is the first and foremost thing we will be identifying while performing our TOV to determine the MCOV capability of my surge arrest. Like MCOV, maximum continuous over voltage. Right? Then the second one is to determine the TOV capability of the surge arrest. So surge arrest will be having two capabilities. So if we check the data, it means we might be know. So one is MCOV capability and the other one is TOV capability. Right? So both the capabilities will be checked during this TOV. As the result, as the outcome of this TOV study is, we will be determining these two, like MCOV capability as well as TOV capability. Finally, so for my temporary overvoltage, right, to check whether surge arrestor is not operating for TOV. Right? So now tell me that why for TOV my surge arrestor should not operate. So TOV is also a one type of overvoltage only. So for this overvoltage, right? Why we should not? Why TOV should not? In TOV, my surge arrestor should not operate. Yes. Yes, TOV will not last long. Should not trip because that overvoltage can be normal after some seconds. Yes, of course. Circuit will be grounded, not really damaged. So yes, TOV will not last long. Right? So usually it will be, so rather than saying in the time period, we can say like the magnitude of the voltage, over voltage. So usually upon occurring this, for example in Faraday effect, so let me say like this, like 1 per unit if I am considering means, right? So if my Faraday effect is occurring means, so we cannot say that voltage magnitude will be go like 2 per unit, 3 per unit like that. Right? So in simple terms, it will be going like 1.05 per unit and 1.06 per unit. So like this only the voltage range will be. Right? That will not affect the proper operation of the system. Right? That is acceptable only. So for example, the generation will be high at that time. So the loads during the peak, after the peak hours, the load demand will be low. So at the time, we can send some little bit Faraday effect. So immediately after the evening time, once again the loads will be getting started used. So at that time it will be decayed, right? It will be completely eradicated. And when coming to LC fault and LLG fault, how we will be considering this means? So we cannot be able to say the duration here, right? For example, LG fault, it can be occur. There is a probability can be clear or cannot be clear, right? But the case what we are going to create here is, so the fault is occurred and it will be getting clear within the standard time, predefined time, so that my system will not face any it will not enter into the emergency state. Right, 5 states, right? In that I am speaking about emergency state. So it will not enter into the emergency state. So like that we will be creating our LG, LLG, and load rejection also the same like that. Right? Then after adding the fault also with the load rejection, LG fault with the load rejection, and LLG fault also with the load rejection also the same case only. Right? We will be mentioning that after some period of time, my fault will be getting cleared automatically, and my system will be coming back to the steady state. Right? So during that very short period of time, right, my system will not face that much over voltage. Why? Because fault is occurring, immediately it will be coming back to the steady state. So at that time, my fault will not be that much it is facing with that much huge impact there. Right? So during the TOV, so upon coming to the conclusion, when coming to TOV, so the voltage rating will not be, the magnitude of the voltage during these events will not be that much higher, and it will not be lasting for a long time. Right? So for this case, if your surge arrestor starts to act means, right? So when the continuous acting of the surge arrestor, previously we have seen these, when we are selecting the surge arrestor rating for these 4 voltages, for this can be occur whenever, so we cannot be able to predict, right? It can occur whenever in our circuit, right? So in that case, it should not be operate. So that will save our surge arrestor, right, from these very small low voltages. These very small low voltages will not create any huge impact in our system. So during this, our system will be in normal state only. After occurrence of these events, our system will be returning to the non-steady state only, normal state only. So that's not a huge issue. Right? So this is the reason. Right? So for temporary period only, yes, TOV can be weeks long. Of course, yes. But even though it is weeks long, it will not be go beyond as I previously mentioned, right? It will be like little bit higher than the nominal range. Like 1 per unit, 1.05 per unit, 1.03, something like that one.
हमारे यहाँ ऐसा नहीं होता हमारे
Yes, it depends upon the country. 10% increase in voltage is acceptable. That depends on the country.
जब आप यहाँ हैं तो यही वहाँ क्या है?
Right. So if there is any question, so kindly don't hesitate to post in chat. Right. All the chat will be saved. Right. So kindly do that. If you are having any questions, kindly post it down. So upon moving to the slow front low voltage, right? So slow front low voltage is also known as switching steady in simple terms. Right? For TOV voltage can be also named as continuous one. So what are the cases we will be creating in our SFO mains? Right? So before that I will be explaining generally. So whatever may be the equipment switching in our power system, all those events will be coming under this slow front low voltage study. Right? It can be whatever may be the equipment that you are firstly switching in our power system, power network, or any power plant. Right? Then all the switching events will be coming under this SFO only. Clear? So in these cases, it will differ from the plant to plant. Right? For example, what are the cases usually we will create? So here also, these basic cases, right? These are the basic cases outline of. Right? For example, my plant is there. So this is this is my GIS. Right? So in here for the DOV, we can perform for the different locations what we need as per the client's requirement. So we can perform, mainly we have to perform in our GIS bus, all these events. So after that, when, for example, this bay is connecting with my GSUT, generator step-up transformer means. So in here also we can able to do all these events, like LG fault in the transformer HV side. Right? Previously we can do like LG fault in my GIS bus bar like that. So depending upon the locations, the cases number will be getting increased here. But by default, these 6 only. Depending upon the locations, the cases number will be getting raised here. Similarly, for transformer energization, cable energization, so not only in terms of energization of the cable, so re-energization of the cable and de-energization of the cable will also be sometimes noted. Similarly, for transmission line also. So it can be energized, re-energized, and de-energized. Clear? So after that, capacitor bank energization, right? Then shunt reactor energization. So switching off all the elements, in simple term, switching off all the elements. Whether you are going to turn on any elements in your power system, all those elements will be coming under this switching steady case. Right? In here what we will observe, right? In here what we will observe means, from the analysis point of view, to determine the protective margin during switching, right? With the help of that protective margin, right? We will be saying that whether my surge arrestor will withstand this switching over voltage or not. For example, if I am switching on my cable or transmission line, right? I am energizing my transmission line. So at that time I will be observing an over voltage. So that over voltage must be withstand by my surge arrestor. So it cannot be directly checked. It will be checked in the form of protective margin. Right? This protective margin. So this my protective margin must be greater than 1.2. So for this calculating this protective margin, right, we will be dividing the value of switching impulse stand level divided by our voltage occur. So when I am energizing my line, so at the time I will be observing an over voltage which will be placed here, and after that the switching impulse stand level of the equipment will be given by the data sheet or the manufacturer itself. So after that we will be calculating this, and this protective margin must be greater than 1 point. So at the time we can say that our surge can withstand. When it is like 1.21 or 1.22 something means it is marginally protective. When it is like 1.9 or 2 means it is overprotection. Right? For example, 1.2 means bare minimum it should be within the value of 1.35 to 1.4. So that is enough for our system, which will be cost effective and everything will be within the range. So selecting 1.9 or 2 is also permissible, but when coming to commercial point of view, it is not acceptable thing. So it will be selecting the higher ratings arrestor will be costing us much costlier, right, than the nominal range. So this is of SFO, right? So is there any clarifications up to now, TOB and SFO? There's a duration I will be coming back. Yes, how to set over voltage setting for protection.
पागल लड़की से यही दिक्कत होता है भाई, उसको हर चीज
Just kindly reframe this. How to set over voltage setting for protection? Whether you are asking about the protective devices or else surge arrestor, do we measure RMS or peak voltage in TOV study? And usually we will use the, I think Stalin is aware about that voltmeter to ground, right? Voltmeter to ground one signal will be there. So that usually measures the phase peak value only. Right? That is depending upon us. Right? We can measure the RMS or else peak. But so far we are measuring the peak and we are determining. Also please reveal the amplitude of TOV in relation to normal voltage. That depends upon the event occurring. Right? That depends upon the what type of event is occurring there. That only we can observe the TOV. Right? Yes. Okay. So then we can move with my fast current over voltage FFO, which in terms also called as a lightning study. Right? So in this lightning study, so we will be observing for two cases. Right? One is direct stroke and the other one is black flash over. So direct stroke means when the lightning is striking directly in the phase conductors of my transmission line, that is known as direct stroke. When it is black flash over, whether it is my lightning strike is striking the tower directly, or else the shielding wire, or else the ground wire directly, which is known as black flash over. Right? Direct stroke means directly it will strike the phase conductor, right, in the transmission line. Black flash over means so it will strike the tower or shielding wire directly, which is known as black flash over. Clear? So this is also similar to my SFO only. Here also we are going to determine the protective margin. Right? So after determining that, I am going to say that whether my surge arrestor will be capable and whether it can be withstand the over voltage occurred when the lightning is happening. Right? That is mine to check whether surge arrestor will withstand my lightning over voltage or not. Right? So these are the first and foremost three studies what we will perform for our insulation coordination. In addition to that, sometimes the transformer energization, it will be modeled as a separate case also. Right? Why? Because here we will be modeling our transformer like a saturable model where we will be with included residual flux also. Right? So sometimes, so this transformer energization will be separately performed, not under the slow front over voltage. We will be separately performing and we will be analyzing about the transformer energization. Clear? So then the fourth one study is very fast front over voltage. So very fast front over voltage usually it will be done when my GAS, it will be usually done for GAS connected system, right? Gas insulated substations. So when it is connected to the GAS and with the voltage rating of greater than 420 kV, so we want to perform our very fast current over voltage study, VFFO. Right? And here are the cases which we will model under our VFFO, like the GIS components. The cases here for VFFO, it is completely GIS based components cases, like disconnector operation, circuit breaker operation, earthing switch operation, and disconnector switch operation. Right? So for this, we have to model our GIS in detailed model. So high frequency dependent model, that model name is usually the GIS manufacturer, right? Who is manufacturing the GIS? They will provide the PS card equivalent for all these components. Like they will provide for both FFO as well as VFFO also. Right? For example, FFO means disconnected switch, everything will be in a simple model. For VFFO, disconnected switch, everything will be like VFFO based model. So those things we want to correct from our OEM only. For the manufacturer, equivalent PS card models we should correct from the OEM. So in here what we will analyze is the same thing only to check whether the selected surge arrestor will withstand very fast front over voltage or not. Similar thing which is similar to our FFO, the same thing I am going to observe here also. Clear? Then TRB, so transient recovery over voltage. So in the previous case I mentioned these four alone. So in addition to that, there are two things. So transient recovery over voltage and ferroresonance magnetic transients. Right? So in this TRB, usually it will be like a transient recovery over voltage. So this will be occurring due to the circuit breaker, sudden opening of the circuit breaker due to any interruption in my circuit, in my power system. Right? See here, in my cases, a circuit breaker opening during fault clearing. So line charging in the, so when my fault is getting clear. So for example, in any system, generator connected system, usually this will be done for my GCB only, generator connected circuit breaker only. Right? So when any fault is sensed, right, and that the circuit breaker is getting open, so during that, it is actually clearing up the fault, right? So during that, the restart interruption, it will be studied in this transient recovery over voltage. Then line charging interruption means, so for example, I am energizing a transmission line, so which is far away from the substation. So for that, it must be energize the lines first, our first line first, then our desired or which line we are going to energize it as a second. So during that time also there will be some interruptions. So there we can study about transient recovery over voltages. Then capacitor bank switching. So this will be coming under both SFO as well as TRB also. Right? In TRB, it will be when the capacitor bank is switched near to the generator. Right? When it is switched near to my source means. So at that time, we can able to see that TRB, the same case, we can able to perform for my TRB case also. Here what we will analyze and observe is to compare with the TRB envelope. So there are some standards for TRB envelopes. So after performing this study, right, I am going to check whether it is within this limit of the envelope. Three different enveloping standards. So whether it is within the limit of that envelope. So in addition to that, to find the peak recovery over voltage, then the rate of restating voltage, RRB. So these two also will be identified using this transient recovery over voltage. Clear? So let me complete this and take up on questions. So you can post it, right? So the ferroresonance. So usually it will be when the inductance and capacitance, when it is not properly configured. So there will be a rising of ferroresonance effects in my power system, like a single phase switching, when without any information, sudden de-energization of my main transformer GSUT, then isolated neutral systems, right? Separate islanded systems when it is connected with the grid and suddenly if it is getting isolated means, right? So in here what we will observe is this is such a simple study only. Like in modeling point of view, it will be little bit differ. So to identify sustained or quasi-sustained over voltages, then in addition with to determine voltage waveform distortion, which can be third harmonic or subharmonic. So when inter and intra harmonics also can be checked in this ferroresonance. Right? These are the major classifications of my insulation coordination. Right? So these are the basic studies that we will be performing in our insulation coordination. Then finally, what are the softwares that are involved for performing this EMT simulations. So our first and foremost software is PSCAD EMTDC. So like in the previous webinar, I have explained why we are going, what are the difference between RMS versus EMT2, why we are preferring PSCAD dedicatedly for my electromagnetic transients, right? So all the advantages we have seen, right? Then so in that RMS, both the modes are also there, RMS and EMT. So in the EMT, we can perform all the things, switching, study, lightning study, all these things we can perform in Power Factory also. Right? Then EMTP RV, then RTDS, real-time digital simulator, then OpenRT. Right? OpenRT is the hardware thing where we have to. So OpenRT, working on OpenRT will took a large time to simulate the basic systems also. But the results, everything we can observe only through mechanically only. Mechanically, what I'm meaning is, in the CRO, we will be observing all the waveforms, everything. Right? But in these softwares, among these, so now we will be performing for, mainly we will be focusing on PSCAD. Right? So is there any doubt up to now what we have seen?
फिर भी सिल्वर
So I
लाइट
think,
चेंज करते हैं घड़िए का
yes, may I get some response? So what are the types of over voltages that can be occur in my power system? Yes, SC abbreviation, which is nothing but surge arrestor. This video uploaded in your YouTube. Let me check with my team. Surge arresters, shielding failure. So those things we can, and coming in detail in FFO, I will explain about the shielding failure, everything. How to select rated voltage of surge arrestor for air-pure and emergency system. So then also we have to perform our TOV, we have to go through step by step, right? After that only we can say that whether the surge arrestor is required there or not. Yes, so we can move forward. Surge arrestor should not operate for TOV means the magnitude of the TOV, the voltage magnitude when it is arising, so it will not be that much higher, like switching or lightning. The voltages, the magnitude are like 1 per unit means it will be the range of 1.05, 1.1 per unit only, which is acceptable only. So with the rise of 1.1 per unit, which will not make the system to suffer. It will be properly operating on our system. So during my TOV, it should not, my surge arrestor should not operate. Yes, so let me go to the slides back. So this hyperlink will direct you to that MyMister map only. So now let me present. So cumulatively we can see this is the generalized representation. Right, TOV, it will be nearly higher, little bit higher only, right, 1.05 or 1.1 per unit only, the increase of voltage, right? So this is the system voltage, basic continuous, and this is my little bit rise in my TOV. So during my TOV, the events, then switching from over voltages, see here, the duration also it will be in the range of seconds, then the SFO will be in the range of milliseconds. So as the time is getting decreased here, so during the switching events, we can say that the frequency will be getting higher here, right? The frequency will be getting higher here. So for this, during the switching events, we should do some changes in our SL. I will explain. Then finally, lightning arrestor, lightning over voltage is FF4. It will be in the time of microseconds, right? We know the magnitude of the lightning arrestor, the lightning waveform, right? The generalized waveform is 8 by 20 microseconds, front and tail time of my lightning waveform. Similarly, for a switching waveform, it can be like 30 or 60 microseconds. Right? So the lightning over voltages we will be observing in terms of microseconds. So during the lightning event, my frequency will be that much higher, like in terms of kilohertz or megahertz. Right? Finally, my VFFO, it will be occurring for my specifically GIS components alone, not for the entire power system. So for the GIS components, I have to model my GIS components in high frequency dependent models. Those models must be provided by the manufacturer or OEM themselves. Right? This is the other representation of the waveform. So in here, see the red one is representing the possible voltages without arresters. The green one, which is in the nominal range of external voltage of the equipment. Then finally, the blue one is the voltage limited by arresters. Right? So in case if it is the without arresters means, see here, this red one. So this one is continuous, which is the nominal system voltage. And this temporary voltage, which is slightly higher than my 1 per unit. So where for this, it can be near, but my voltage limited must be, the surge arrestor should not operate, right? So the surge arrestor rating must be selected higher than this rating. Clear? Similarly for my switching, so this is the over voltage, possible voltage without arresters. So withstand, it will exceed the withstand limit also. So when I am placing my arrestor, the voltage is completely suppressed during the lightning event. Switching events. This is finally the lightning events. So it can be go beyond this 5 per unit also due to its higher magnitude. Right? So after that, after going beyond that 5 or 6 per unit, the magnitude of voltage, so upon placing the arrestor, it can be limited, like up to 2.5 to 3 per units. Clear? So these are the with the reference of this standards only. This is IEC 60071 standard. So in that, the table 2 is representing what are the events to be created for what are the cases. See here the OVSF4, FF4, VFF4. So all the cases what I have mentioned here, like in the mind master I have mentioned, right? So all these cases, right? These cases I am not mentioning blindly. So all these cases are taken from my standards, and with the help of the standards only, I am creating the cases here. Clear? So for TOB, load rejection, transformer energization, parallel line resonance, coming to here, line fault application, fault clearing, line energization, de-energization also applied here, but we will be bringing it to, it can be done in both the cases, see here, but we are bringing them to my SFO. Clear? Similarly for FFO, see backlash shower, direct lightning stroke, and my FFO switching inside GIS substation. See here, which means the GIS dedicated for GIS components. Clear? So this is standard installation levels. So now let me go to the TSCAP model and show you something. So TOB case I have already prepared for this webinar. Right? TOB means nothing but we are going to perform temporary over voltage, right? Like current effect, fault, load rejection, LG with fault rejection, LLG with fault rejection, or load rejection, right? So this is how we should model the network for my TOV analysis. Right, where starting from the source. So all the substations, everything, it will be modeled as source here. Right, in our PSCAD, we will be modeling the entire substation, remote substation, everything. We will be modeling like the grid here, power grid, that is source. So following that, there are two cable feeders. So CS1 and CS2. Two cable feeders are connecting with my GIS. So this is my GIS. So for each study, there is a restriction that how to model each element. So this is the simple model, which is known as bisection. So similarly, let me open the SFO also, so that I can, sorry. Just a second. This screen got stuck, just a second. So in this, let me take the SFO case here. The same SLA only. So for different types of study, we have to model like a different one. For example, this is the cable feeder for which I have modeled for my TOV. This model is known as the simple model bisection. The same cable feeder. So this is known as frequency dependent cable, where we will be modeling the exact cable which is present in our real time. The same cable we can model like this. With the help of the cable datasheet and cable configuration, we will be modeling the entire cable similarly which is present in our real time. Why? Because we have to observe the frequency dependence thing. So this model is known as frequency dependent model, where we will be modeling the cable in detail. Right, in follow with, this is my GIS. So GIS usually it will be having more number of elements, right? Like disconnector switch, switch, everything. But in this case, we will be modeling our breaker only. So only breaker, even that is for also opening and closing our operation alone. Rather than that, we will be not modeling like a detailed model. For protection purpose, we won't model. We will be modeling this breaker just for opening and closing action. Right? Why? Because we want to do energizing, de-energizing, everything. So for that, my breaker must support opening and closing actions. Clear? Then, following that, similarly the cable also. See here, this is bisection for this cable which is connecting the transformer. This is my main transformer, GSUT. So which is connected the first way of my GIS through the line. So like this, we will be creating the case. So this is actually the LLG fault with load rejection case. So see here, how I am saying is, this is the fault component. I think if someone attended the previous session, you might be aware. So if not so, we are going to discuss these things in detail also. Right? So see here, this is the fault component. Like in ETA, we cannot able to directly fault the bus, and we entering into the short circuit study mode, and I will be performing this. Right? So in here, this fault logic will be, I will be using for creating the fault in my circuits. And this is my load. Equivalent load I will be modeling. Right? Equivalent load I will be modeling. And this breaker is for just opening this. Why? Because I am going to perform my load rejection case. This is my load. Now this load is getting to be rejected means this breaker is getting open means which is the meaning of load rejection. And this AB to G means double line to ground fault in this case. So LLG fault with load rejection case. I am performing like this. for my TOB. Like this, I will be performing for different cases for different locations. I have to model up to the GSUT alone, and in case any additional unit auxiliary or excitation transformer, any auxiliary transformer, submesh transformer is there means I will be modeling that also. Rather than that, modeling up to the MV side is enough. In case if it is a transformer means 3 winding means modeling up to the LV1 and LV2 range is enough. Clear? So the same case only when coming to SFO, the same system only, I have to model the surge arrestor also in this case. Why? Because in the previous case, my surge arrestor will not operate. Right? There it should not operate. With the help of the calculations, I am going to calculate whether my surge arrestor will operate or not. If it is operating, I have to select the next rating of my surge arrestor. Right? When it is coming to here, I will be modeling the frequency dependent model of my surge arrestor. So we can discuss everything in detail. Right? Not in this session as of time due to time constraint. So this is known as frequency dependent model of my surge arrestor. So why I am modeling the same surge arrestor like in detailed manner means I have to capture the frequency dependent oscillations. Right? Why? Because during these cases, my frequency will also getting disturbed during my switching as well as sliding events. I am surely why? Because the occurrence time is very low. So when the time is low, we know that the frequency will be very much higher. Right? So during this case, to observe the frequency dependent behavior, I am going to model the surge arrestor also like this. Then my cable or line, whatever it may be present, I am going to model like this in the exact replica of my real-time model, which is the equivalent of my real-time model, which is known as frequency dependent model in my PSCAD. Clear? So upon running all these things, I will be observing everything. Right? So now, yes, recordings, everything will be, our team will be noting all these things. Yes. So now, up to now, is there any doubts? Yes, so in this case, also can we perform relay protection in PSCAD? Yes, we can perform. So in the master library protections, you can see all the relay modules are present here. Impedance zone elements, out of step OOS 68 elements, inverse time over current element 51, 87, 32Q. Or else the reserve protection is not there means we can include them as library file as well from external source. We can include them and we can perform here also. What will restrict you to perform is the record detail, the data requirement is much more. Like when you performing in the ETA, so this is not similar like ETA. You need much more data to perform the relay coordination, but we can perform all the steady state also we can perform, like load flow, short circuit, protection coordination, harmonics also we can able to perform here. The only thing what will restrict is the data requirement will be very precious and many more data will be required here for modeling and validating and performing everything. Yes, post the questions continuously, so I will be noting. So the latest version as of now is, that is what we are having. 5.0.2 is our latest version of PSCAD, and they are releasing some updates for this version 5.0. Right, let me stop sharing. So is there any clarifications up to now what we have seen? So because due to time constraint, right, I'm stopping here and I'm